Everyone is talking about how powerful LLMs are, and yes, they are. But in the enterprise, power isn't the whole story. You need reliability, you need governance, and you need to trust what it does. Because a hallucinating chatbot might be annoying, but a hallucinating database agent, that's a disaster. In the enterprise, it's not just about what AI can do. It's about how safely and reliably it integrates into the system that run your business. So how do we bridge AI flexibility with the determinism required by enterprise systems? Natural language with a production-safe behavior. That's what this series is about. From prototype to production, real-world AI systems, secured, structured, and ready to deploy. AI beyond the hype. Today's project, you've all seen LLMs generate SQL. But today, we're going a step further, building a schema-aware agent that belongs inside of production systems. It uses prompt engineering, schema validation, role-based access control, and query sanitization, all to ensure the query you see is the query that runs. It's built in Python and it's open source. So whether you are an engineer testing LLMs, an enterprise piloting AI-assisted data access, or just looking to use AI responsibly with structured data, this system gives you a real-world foundation to build on. I've done the hard work up front, so you can explore, extend, and make it your own. Let's dive in. And no need to take notes. Everything you see today, including setup instruction, is linked in the description box below. All right, let's walk through the architecture behind the system, how it integrates LLMs with the traditional software patterns to generate SQL safely. At the core is a schema-aware LLM-driven query engine designed to support AI-assisted querying without sacrificing security, governance, or control. This is the brain of the system. It takes in SQL generated by an LLM, then validates, filters, and enforces security policies before anything reaches your database. Built-in safeguards include role-based access control, or RBAC, which filters access by user role, role-level security, which enforces record-level access policies, SQL injection protection, detecting and blocking unsafe queries, last but not least, observability and governance, which captures audit trails and policy violations, if any. This isn't just prompting an LLM and executing blindly. It's a controlled production-grade systems. While the query engine handles validation, it still needs an LLM to generate the initial SQL. That's where the LLM client comes in. It's an abstraction layer that lets you switch between different providers without touching the business logic. If a model fails, it fails gracefully. If it succeeds, the result still passes through validation before execution. AI may suggest the query, but the system decides if it's safe to run. Now, the query execution is controlled and safe. Once a query passes validation, it is sent to the database for execution. The system validates and checks that only authorized queries based on role, no destructive operation, only read-only access, and then full audit logging for compliance. Even though an AI model is involved, the execution remains deterministic. No surprise, no risk of data corruption. The system exposes two main interaction layers. First is an API mode through the Ask interface for direct, stateless query generation. The second is an agent mode through the chat interface, which is a conversational interface with memory and refinement. This makes the system usable in multiple contexts, whether you want to use it through your backend services or through chat-driven UIs. For the UI, we have a UI layer that you will see for the walkthrough. I'll be using the chat UI, which connects both the API and the agent interfaces. It lets us ask questions in natural language, and then the system will use the LLM to generate a query, validate it against the schema, RBAC, and guardrails. Then, if it's authorized, it will safely run it on the database. Now, why this matters is because most AI demos skip past safety. This one starts with it. The LLM is integrated, but not in charge. And that's how we bring AI into software engineering, without compromising your precision, security, or control. Now that you've seen how the system is built, let's see it in action, from data to query to response, all in a real enterprise-style workflow. First, let's look at the database. We're using Northwind, a classic sample database. It's running in a local Docker container that ships with the project. So you can spin it up quickly and start testing right away. Northwind simulated a small ERP with customers, orders, employees, products, and suppliers, all linked through realistic relationships. Here's a schema diagram for reference. Notice the different tables and notice also the relationships across the tables. With that in mind, here is the plan. We'll start with basic natural language queries and gradually build up to advanced capabilities, including role-based access control, memory-aware AI refinement, and secure SQL generation. Under the hood, this system is using Fast API to expose all core capabilities as REST endpoints. Whether you will be using the Ask endpoint for stateless queries or Chat endpoint for memory-aware sessions, both are fully documented and accessible via Swagger UI at /docs. I've also built a lightweight front end using a Streamlit, a chat-style interface that makes it easy to interact with the agent, while still enforcing all the same back-end logic and security controls. I will be using the agent mode through the demo, but please feel free to try the API point through Swagger UI or the chat interface. Let's cover some concepts first. In real production environment, user permissions would be handled by your IAM provider, like Okta or Azure ID. For this demo, I've simulated that using a simple config file so we can see how role enforcement plays out. Nothing fancy, but we list tables and columns permitted for each role, as you see here. I also set a role to the user here, which will determine their permissions. Now let's begin the demo as an admin user, which has broader access. And before diving into the access control, let's look at how the system handles complex natural language prompts without needing exact phrasing or SQL knowledge. I'll start with asking to compare total sales by employee for the first quarter versus second quarter in 2024 and highlight employees with highest increase. This requires filtering by 2 time periods, grouping by employee, and computing totals across orders. The agent generated a multi-step query that handles it correctly. No template, just a schema and a prompt structure. Let's try another. List customers who haven't ordered in the last 90 days but have spent more than $1,000 total. This request combines a time-based exclusion with a historical spend filter across multiple tables. The system identifies the correct joins and constraints and still routes the query through the validation and access layers. These examples show how the agent can interpret and structure more advanced queries, not just answer simple lookups, while still enforcing governance and producing transparent SQL. Let's make another request. List top 5 selling products by dollar amount, include supplier name. And notice that it displays the supplier name for products, which we're going to come and touch on that later. Now let's list all orders from last year. Notice how it shows orders from all salespeople or employees. Let's move from standard queries to more secure behavior enforcement. Let's take a look at how context is enforced. We'll ask the question, who won the Super Bowl this year? Notice how it didn't answer because it's out of context. Here's another example of not allowing destructive queries. Let's ask the system to delete orders table. Notice how we get access is denied. Now let's test how it defends against unsafe inputs. Here's an example of protecting from SQL injections. Select start from customers, semicolon, drop table orders, and we see that this was blocked by the sanitizer module. Next, an example of memory-aware AI refinement in the agent interface. I'm going to say show all orders placed in 2024, and we can see our data here. And then we're going to ask to filter them by customers from USA. And finally, we're going to ask to group the results by employee. Notice how the agent remembers context from question to the next. No need to repeat information. Now let's try an example of vague request. Tell me about large orders. And we see that rather than guessing, the agent asks about what is considered a large order. Now let's reference a non-existent table. We're going to ask the question to show expenses by month. We will see that the agent will not answer. No hallucinated queries are executed, thanks to schema validation. Now I've switched the user role to employee. Behind the scenes, this updates the config file and restarts the backend again. Nothing fancy, just simulating a different user session. Let's submit another request. Show all orders placed in 2024. Since I'm currently running under employee mode, the RLS kicks in and only show me the records that I have access to. Next, I'm going to ask the request to list top 5 selling products and include supplier name. Notice that because employees don't have access to supplier name, the LLM determines I don't have permission to access this data. This is schema level access control, enforced not at the UI, but at the query generation layer itself, right where decisions happened. RBAC in this demo is file-based, but the same rules can be wired into an IAM or a policy engine in production. If I open the logs or terminal, you'll see real-time activity, successful query execution, sensitive data access, blocked access attempts, and sanitizations warning. In production, these logs would feed into your audit and monitoring pipeline. Before we wrap up, you can call the Ask or the Chat APIs from external dashboards. You can swap LLM providers easily via the config file. You can also connect to any SQL compatible database, not just Postgres and not just Northwind. The architecture is modular, extensible, and enterprise ready. That's the demo. We turn natural language into safe schema-aware SQL, with access rules enforced in real time, and every step is logged for audit. That's the kind of AI that fits enterprise environments. If you have questions or want to extend this project, drop a comment. I'd love to see what you built, and let's keep building. In this chapter, I'll walk you through how to install and run the schema-aware AI SQL agent locally. We'll follow the same steps outlined in the README file, but I'll show you how to set up your environment, configure access, connect to your database, and launch both the backend and the front end. Setup takes about 5 minutes and works on macOS, Linux, or Windows. Let's just start by cloning the project and preparing our environment. First, create a directory for the system. In your terminal, run this command on the screen. Make directory AI for the enterprise. Now let's move into that directory we just created. So we're going to change directory for AI for the enterprise. Then clone the repository using URL on the screen. URL is also in the video description. Once it's completed, let's change directory to the repository root folder. So we're going to change directory to schema-aware AI SQL agent. Now create a virtual environment. This is optional, but I highly recommend it to avoid dependency conflicts, keep a project isolated, and make dependency management easier. So we're going to issue the command python 3-m vnv vnv. Next, we're going to activate the virtual environment, and we're going to issue the command source vnv/bin/activate. If you're on Windows, you should call vnv/script/activate, and then we will install the required backend dependency. So we're going to issue the command pip install-r requirement.txt. Depending on your connection, this shouldn't take more than a few seconds to finish, but you can see the progress as it goes on. That gives us everything needed for fast API, LangChain, SQL Alchemy, and more. Next, we configure environment variables. In the project's root, copy the .env.example file to a new .env file using the command cp space.env.example space.env. Then open it in your editor and update the following values. Database URL, which is the connection string for your database. Open API key and or open router API key or other credentials for your LLM provider. These values are used by the agent and backend at runtime. Now open the config YAML file located in backend utils folder. This is where you define role-based access control, the RBAC, the row-level security, the RLS filters, sensitive columns, LLM provider and model settings, and memory behavior for conversations. This setup simulates IAM behavior in production environments, but it's easy to edit locally for testing. Let's talk about the database. You have 3 setup options. First, you can use your own Postgres, MySQL, or SQL Server, or any other SQL compatible database. Or you can load the Northwind schema into a local Postgres instance. Script included in the Northwind SQL file under database folder. Or the easiest, run the included Docker container, which comes preloaded with Northwind. Now, if you are using Docker, then switch to Docker folder by running cd space Docker. Then run the command docker-compose space up space -d. This spins up a ready-to-use Postgres SQL container. It automatically creates the user, password, and a schema for you, so there is nothing to configure manually. Once that's in place, the backend can connect, introspect the schema, and start responding to natural language queries. Let's start the backend server. First, we need to navigate back to the root folder. So we're going to issue the command cd space ... Then start the server by issuing the command that you see on the screen. Give it a few seconds. Then open your browser to http localhost port 8000/docs. This loads the built-in Swagger UI, a quick way to test API endpoint. Now let's launch the front-end chat interface, and we're going to use the command that you see on the screen. If it doesn't automatically load, open your browser and navigate to http localhost port 8501. Here you can enter natural language questions, view the generated SQL, and switch between API and chat modes. A few quick tips if something doesn't work. If you see module not found error, then run the pip install-r requirement.txt. If the backend can't connect, check your database URL and make sure your database is running. If chat interface doesn't launch, ensure your virtual environment is activated and you are in the right directory. If you receive connection refuse error, then check if your database credentials in the .env file match your local setup. Still stuck? Make sure all dependencies are installed and services are running. And remember, you can always delete the parent folder and start the whole setup again. That's it. The agent is now fully installed and running locally. If you can access the UI at port 8501 and the API docs at port 8000, everything is working. In the next chapter, we'll explore the code base, how prompts are processed, how validation works, and how SecureSQL is generated. Let's explore how the agent works behind the scenes. In this walkthrough, I'll cover the project structure, configuration files, and core modules, so you can understand how to use it, adapt it, or extend it in your own environment. Everything here is built to simulate a production-like setup. In a real system, components like authentication and access control would connect to your IAM provider, enforce policies dynamically, and log in actions for auditing. Full documentation is available in the project README file, including setup instructions, environment configuration, database options, and API usage. Whether you are running it locally or integrating it into a larger system, you'll find everything you need there to get started quickly and confidently. At a high level, the project is organized into three main folders. Backend folder, which contain agent logic, API endpoints, utilities, and configuration. Database folder, which contains the schema parsing code, SQL generation code, and validations. And a front-end folder, which contains a lightweight web chat UI for interacting with the system using a Streamlit library. At the root level, you'll find the .env file for environment variables and requirements.txt to install project dependencies. As for config.yaml for access control and system behavior, you'll find it under the backend utilities folder. The .env file is where you define your database connection string and API keys for your LLM provider, whether that was OpenAI, OpenRouter, or local models like Olama. The config.yaml file controls system behavior. It includes role-based access control RBAC, row-level security RLS filters, sensitive column filtering, memory settings, and your selected LLM configuration. In a production environment, configuration values would typically be pulled from a centralized identity or policy platform rather than stored in files. Here, they are defined locally to simplify development and testing. If you're not going to use this option with the included Docker container, make sure you update the .environment file with the correct database URL, and the agent will connect and introspect the schema automatically. Inside the API.py file and API folder, we define two endpoints, Ask for stateless single-turn query generation, and Chat for conversational memory-aware sessions. All requests use the authenticate user function, currently mocked for local testing, but built to integrate with your IAM provider in production. Based on the endpoint, requests are routed either to the AI agent or directly to the query engine. The agent lives in AIAgent.py file inside agent folder. It supports both stateless and memory-aware modes. If max memory length is set to 0, it retains full conversational context. Otherwise, it uses a sliding window to manage memory. Interactions are stored and serialized using Python SPICUL module, allowing persistence across sessions. This enables better handling of follow-ups, clarifications, and query refinements over time. In the current context, I only persist the queries, but not the results, since they may include hundreds, if not thousands, of records. In the LLM client.py, you'll find the LLM client abstraction. This module encapsulates the logic for interacting with different LLM providers. It supports OpenAI, Hugging Face, OpenRouter, and local models like Olama. You can switch between them simply by updating your configuration, so go and try them. For models that support it, I explicitly set temperature to 0, prioritizing determinism over randomness. For local models, I've included performance-enhancing settings like CPU thread counts, reduced context size, and output limits. This separation keeps your core logic independent of any one provider, making it easier to experiment between models and migrate among them. The schema-aware SQL.py file under database folder is where natural language gets translated into validate SecureSQL. The main function is a process query, which coordinates other helper functions, such as generate SQL query that builds the prompt and parses the SQL output, and validate a query, which ensures SQL syntax and confirms the schema alignment, and query safe and authorize function, which checks user role, filters access, and blocks unsafe statements like a drop, delete, or unrestricted update, and execute SQL query function, which runs the query safely after all checks. At runtime, the schema is introspected and passed into the prompt, giving the LLM contextual knowledge of table names, columns, and relationships. There is a placeholder function to call another model to validate the query quality if needed. You can use the same, but I recommend using different models. Security is enforced throughout the stack. RBAC filters which tables and columns a user can access. RLS applies row-level access rules tied to user identity, and sanitization to prevent dangerous SQL from ever executing. These guardrails ensure that the queries stay within clearly defined boundaries, and that the agent respect enterprise data governance. One of the most important parts of this system is the prompt itself. Before the LLM ever generates SQL, it receives a structured prompts crafted with contextual awareness and engineered with guardrails and rich context. This includes a natural language question, the user's role and permissions, a full schema snapshot tailored to that role, and clear instructions like only generate selected statement, or ask for a clarification, or return access denied when needed. This is not a plain text prompt. It's a structured, data and rule-driven instruction set that helps the model behave predictably and stay within boundaries. If a request is too vague, like tell me about large orders, the agent asks for a clarification instead of guessing. This approach reduces ambiguity and improves both safety and accuracy. It's how we bridge flexibility and determinism. The user can ask natural questions, but the LLM is guided to generate only safe authorized SQL, with no hallucinated joins or unsafe operations. You can view and customize the prompt logic directly in the schema-aware SQL.py file inside the generate SQL function. Make it fit tightly to your needs, database, and data. In chatui.py file in the front-end folder, I use Streamlit to build a lightweight browser-based chat interface. Users can select between API and chat modes, submit questions, and view both the generated SQL and the query results. It's a no-code way to interact with the system, making it easier for analysts, testers, or product stakeholders to explore functionality without writing SQL. It can also help engineering teams generating optimized and efficient queries, as if they were SQL experts. This system is designed to grow with your needs. Swap out LLMs by editing config file, plug in any SQL-compatible backend, or customize the prompt logic, memory behavior, and access policies. This modular design also makes it easy to integrate into larger internal platforms, such as dashboards, portals, or data services. That's the core code base. It's built for clarity, governance, and real-world extensibility, with patterns that map directly to production systems. Whether you're prototyping a secure internal data agent, building tools for analysts, or exploring how to safely apply LLMs to structured data, this project gives you a practical foundation. It's more than just a demo. It's a system designed for engineers experimenting with LLM workflows, data teams needing role-aware governed access, and organizations piloting AI-assisted SQL with the safety controls production environment demands. So whether you are validating data, automating reporting, or building internal tools, this is a base you can build on. Of course, not all schemas always fit in a single prompt. Some databases grow with hundreds of tables and relationships. LLMs start hitting real limitations, like token caps. Even large models top out, as of today, around 4 to 32K tokens. Performance overhead, sending the entire schema slows down response time, or relevance issues. Most queries only touch a few tables, yet the model sees everything. But here are some ways to evolve the agent and handle large complex schemas more effectively. You could use dynamic schema extraction by sending only the relevant part of the schema based on what the query actually needs, vector-based indexing using tools like Face to embed and retrieve schema chunks on demand, and hierarchical schema summarization, which group tables into logical blocks and describe them at a higher level using AI-generated summaries, query optimization feedback loops by tracking which columns and tables are queried most often, and prioritize those in the prompt context. These are strategies help LLMs stay focused, efficient, and aligned with actual usage, while keeping control in the hands of your system. And here are some natural next steps for extending these systems. You could add retrieval augmented generation RAG for smarter prompt injection, or fine-tune LLMs on your own domain-specific SQL styles. Set up observability with logging, metrics, and alerting. Implement caching and autocomplete for common query patterns, or add visualization support for quick data exploration. All of this moves us closer to an AI layer that is not just powerful, but predictable, where AI becomes a governed, auditable, and explainable part of your software stack. If you have questions about setup, code, or architecture, I'm active in the comments, so chat with me below and I'll do my best to help. And if you enhance the project, whether it's a smarter query logic, UI improvements, or backend integrations, I'd love to see what you build. This is just the start of bridging LLMs and production-grade software systems. Thank you for watching. If this was helpful, click like, and click subscribe if you'd like to see more, and let's keep building.